Good day, everyone. This is Hamak Yingli, your Quantum Odyssey tour guide. Merry Christmas to everyone, and this is an especially memorable Christmas as the date is a symmetric 25/12/25, especially if you're in Japan, China, or if you're like writing the date time in UTC. This Xmas is an especially memorable one also because it marks 100 years of quantum science and technology. And the image there is an official, let's say, as on the History Channel image, poster image of Christmas. At least. But also, we're over 50% of the way through the 2020s. Time runs fast, and technology runs fast. Don't know if this stocking image is AI generated or not, but today I and my family went to the church, and unfortunately, we saw some AI slop. Well, can you see any AI content in this video series, this 50-day series? Maybe? So, here's our board diagram. This thing represents the main mode, the campaign mode of the game. So, it is the learning path of the game. We first start with the basics, namely how the game works initially, and then the most basic gates, before we move on to combinations of gates, more emergent properties, and then the quantum phenomenons and basic quantum algorithms, and a few challenging problems. There are other modes in Quantum Odyssey, namely you want to solve player-based faults. Then there is play ranked, which you have to complete player-made challenges, which they might be considerably more difficult and longer than the campaign nodes. So campaign nodes are puzzle sets. And there is also called the Forge mode. So Forge, which allows you to create new puzzle sets and events. And of course, resonance is just another word for settings. So this marks the nearly 1 year anniversary of Quantum Odyssey Burp EA, called Early Access. Quantum Odyssey is expected to exit early access in 2026, and there has been several updates to the puzzles, including a new puzzle regarding the swap gate, and as well as the updated tutorials, which they have all been live streamed, and a few of these more challenging catch-all puzzles, which are the red nodes. This is an overview on the game mode of Quantum Odyssey. As of now, there are over 5K registered users in Quantum Odyssey, and maybe like a few dozen. So a few dozen daily at any active time. So there is definitely some room to improve, and of course, leave a review on Quantum Odyssey. Again, if you have checked one of these early 50-day challenge videos, so I'm intending to remake the 50-day challenge videos. The main criticism are Quantum Odyssey is difficult, it is confusing, it is colorful like the Rubik's Cube, but it will take a while for you to get this, so you have to learn. Is it informative? The best answer is maybe. Maybe you still need to Either treat this as a puzzle game like chess or the Rubik's Cube, or you can treat it as a legitimate way to learn quantum information. Is it useful? Well, it's also useful not only for quantum computing, but it is also for understanding how linear algebra works. And my 50-day tutorial would also help you apply linear algebra and complex analysis skills. Is it a tutorial? Yes, it is a tutorial, but how you present Quantum Odyssey kind of matters. Okay, it's fine if you treat this as a puzzle. It is fine if you treat it as a learning tool for you to learn quantum mechanics or quantum information and you want to get more into it. There are plenty of resources. I am an IBM Qiskit advocate, so IBM Qiskit advocate. So that means this new 50-day challenge, which unfortunately one of the earliest ones would have to be backdated. Yes. So this Xmas is an opportunity. Tutorial refund rate. Yes, everyone's busy. They're preparing for the holidays. The summer vacation if you're in Australia, winter vacation if you're in the northern hemisphere. Refund rate, we want to reduce that as well. And of course, the learning pyramid. Like, you cannot build an app if you didn't build like something rather crappy at first, because real learning actually is beyond the books. You actually have to really actively participate. There is no exceptions to that rule. Of course, like I would say, like it's like 70% of the stuff is hands-on. Then let's say 20% is peer discussion, so social learning. Then 10% is, let's say, it's solo formal training. Would be over there. Might be more, especially if you are somewhat stuck on some things and you need to realize how to fix this particular weakness. Maybe you can add some more solo time on that. But please, please do not cram. Do not cram. So let's show a brief overview. So what does Quantum Odyssey teach you? It teaches you linear algebra. So actually, if you know a lot of linear algebra or apply linear algebra skills, then Quantum Odyssey will be significantly easier. So why linear algebra? Linear algebra really, let's say people introduce this as matrices and vectors. Well, what is matrix multiplication? Matrix multiplication is the most important operation in linear algebra. But it just basically says output from input. And it is linear. Each output is a linear combination of the inputs. Let's say over there, 1, 2, 4, 3. So x from x to y, the new y is twice of the old y. The z becomes 4 times the w, so it takes 4w to make the new z. Then the w slot would now be 3 from the z slot. So x, y, z, w from x, y, z, w. Classical physics, so that is, say, the Newtonian, Lagrangian, and Hamiltonian mechanics. That is the physics you learn in high school. And then the physics that's based on differential equations and, of course, calculus. Classical computation, which is just one part of computer science. The earlier part of the other one is software engineering and app development. Quantum mechanics, quantum information, of course. That's what Quantum Odyssey is about. And Quantum Odyssey. But here's the crux of the problem. what is Quantum Odyssey? And here's a more important question. Why Quantum Odyssey? Why Quantum Odyssey? That's the big thing. So I would answer why quantum. What is Quantum Odyssey? Quantum Odyssey is a visualization tool for visualizing linear algebra and how this applies to quantum computation, including its intermediate steps, and why. It allows you to visualize and instantly verify that your calculations and your linear algebra is correct. It allows you to visualize using colors on the linear algebra and the complex analysis involved with quantum computation and how this turns into parallelism. Because the X gates, you're basically applying the X's on pairs of wires in parallel. Then what is quantum mechanics? So you want to know what's quantum mechanics. Well, why the word quantum? The word quantum simply means discrete amount or just amount. In fact, the very word is used in legal vocabulary and classical computer science. For example, administrator defendants then use a computer program to allocate to the participant sufficient software licenses the value equal to the quantum specified in the information format. Oh, and that's straight from a legal court record in Ontario. And the other one is a quantum of time, which applies to time sharing operating systems. And that's classical computer science. Now we're gonna go into what everybody thinks of when they hear the word quantum, because it's most famously known in physics, and that we are latently rely on quantum mechanics, especially the macroscopic phenomena, to power our modern world. In fact, magnetism comes from quantum mechanics. And if, of course, anything like that's obvious, like superconductors and levitation, that's quantum mechanics. But on your very LCD screen, the spectrum of a star, which identifies the chemical composition of the star and whether it is evolved or not, and of course, nuclear reactions and radioactive decay is also based on quantum mechanics, because at that scale, you only see discrete outcomes, whole number multiples of an elementary quantity, and if it happens that it's not, then if you do observe, then there's a probability that it's either there or not there. So that's how we get our states, which is written as a ket. Like, let's say it's 0 or 1 when we have like isolated particles. But when we have like 2 or more, we have like something like 0, 0, 0, 1, 1, 0, and then 1, 1 for 2 qubit system, which could be like, let's say, 2 electrons, 2 neutral atoms. But also, let's say, we can measure a qubit in another axis, like plus minus, or like a combination thereof. Like that's called the x basis. The computational basis just called the z basis as well. And the basis value is really like based on the eigenvectors. But ultimately, it's still like the positive eigenvalue and the negative one. And interesting enough, the 1 is given the negative eigenstate. Quantum mechanics, the small scale discrete thing and states not in these discrete are in superposition, which leads to truly probabilistic random behavior, which hopefully we can truly secure our data and resist RSA. We can use the atom and entanglement to implement exponential parallelism. For example, we can entangle a qubit to form, let's say, the Bell state, which is the equal superposition of the 0, 0, 0 and the 1, 1 state. So and then each of them have, let's say, an area of half. That means its radius is 1 over root 2. And this can be visualized through the Quantum Odyssey interface. So here's the rules of Quantum Odyssey. And here is an example over there. So Quantum Odyssey is essentially a puzzle game. So it is a puzzle game like Rubik's Cube. You start with, let's say, like a given state, which is represented by an array of sigils. So let's call this state psi 0, state psi 0. You start with a sigil. Let's say in this case, let's say it's equal to the 0 state, the 0th state. That means all observations lead to all 3 qubits being 0. It's not necessarily 0, 0, 0. It could be like any others. And then our goal is to use the available gates and place them onto one of these slots to ensure that the sigils split, merge, or change colors such that it matches the bottom, which is, let's call this psi of 1 on the bottom over there. The number of wires is 2 to the power of the number of qubits. So in this case, the qubit, there are 3 qubits. The qubits are numbered from, let's say, in descending order. Let's rank them in Roman numerals, like qubit 1, qubit 2, qubit 3. But we can also like do it in place value, like ground qubit. So ground qubit, first qubit, and then second qubit. Please remember this convention. When I say a qubit by an ordinal number, including ground, that means you're going from the least to the most. When I say it straight by the number, like a nominal number or Roman, then it's from the leftmost to the rightmost. So qubit 1 is not the same as first qubit, so please remember this confusion. So least significant qubit, least significant bit, or most significant bit. So please remember this convention in my future videos. Here is an example. You start from the 0 state. That means the only sigil is a full-sized sigil placed on the 0th slot. And you have to use the supplied gates. There's an unlimited supply of these gates to rewire the wires such that it is to be split, merged, or color changed in a way that that when the sigils reach the bottom, it matches what the bottom is expecting. Okay, so let's go with this example. The first, we need to add an H to split the sigil into two sigils. Let's do this on the qubit 3, so that's the ground qubit. So we have the H. So the H, so notice that for a sigil, for an individual sigil on the left, it splits into two equally sized but half-sized sigils and equally colored sigils to the that on the two slots that only differ by the qubit 3, the ground qubit. If there are sigils on the both sides, then there is a split and then there is also a merge. And the merge is additive. That means any imaginary component and real component would combine, they would not mix. Reals and reals would add together or cancel out depending on their signs. So we have an H there. Now we perform a Y gate. So we add a Y gate over there. The Y gate is the last of the basic gates that you will learn. The Y gate is like a combination of X and Z plus an imaginary global factor. So the sigil that advances from 0 to 1 also advances in phase, so it's green. So the color can also mean advance or retract a phase, just as it means current phase. So that's like group terminology. And the sigil that goes back from the 1 slot to the 0 slot qubit on the uncommon qubit over there, so that's these pairs of lines. We therefore end up with yellow on the 0 slot, the 0 state, and then a 1, and the green on the 1 slot. Finally, we add a C gate. So we have that's a C. That means the sigil, only the sigil on the right of the pair, right pair, would have the gate applied. In this case, we want the other two qubits to also switch to the 1, but only for the right. Otherwise, we're doing both in parallel. We do the C, then we do the X. The two X's over there. So From there we have x. We also need to notice that there's another pair that's also applies as well. So 0, 1 and then 1, 0 would also apply as well. Themes of parallelism will also happen. So in this case, you are performing two x's in parallel. This is called a tensor product. Tensor products basically reduces a multi-qubit operation into single qubit operations. So we saw a parallelism over qubit 1 and qubit 2. So first qubit and second qubit is parallel. But other than that, we see like an HY is serial, HYC is serial. Our solution has 5 gates and a depth of 3. After completing the puzzle, you will be scored based on time and the number of gates you have used. Ideally, you want a gate that is shallow because in a real qubit quantum computer, errors will accumulate and they accumulate exponentially, if like compound interest. But interestingly enough, it does not penalize you for using like more expensive gates like the T gate or non-native gates. This is the overview of the rules as I've explained them as clearly as possible. But if you really want to experience the game, you will have to try it out. You will have to get hands-on. So let's discuss about the basic terms and the most basic theory, the Born rule. Quantum Odyssey is a visualization tool for how probability amplitudes switch, split, or merge when subject to quantum gates. You will see this demonstration through my live streams. Last summer. The diagram over on the right is the color that represents the sigil amplitudes. Namely, if the sigil amplitude is a solid color, it's one of these 4. If it contains equal parts of imaginary and real, then we call this a yin-yang. And otherwise, it's called an eye. So yin-yangs are slightly harder to deal with, but eyes are the one that are considerably more difficult to deal with. And then there's the sizing issues. Because for eyes, it's basically a larger of the two components beneath the smaller of the two components, which can be slightly deceptive. And then there's something called group theory, which you might have been using it implicitly, but I teach you like explicitly how this thing works. But it basically is like an operation, like the colors can mean both the phase and how to change the phase from positive real. The arrows over there is the action on how it affects a solid color sigil. For example, a green, only a blue wire would cause the sigil to have its color unchanged. If it's on the green wire, it would cycle from blue, green, red, yellow, and so on. Opposite direction for yellow. For red wire, it would alternate from blue to red to blue to red, or green to yellow to green to yellow. So that's the something called a Cayley diagram, Cayley graph. Again, a sigil is a probability amplitude in the z basis. Specifically, like 1 on the one of these 2 to the n wires or slots, let's say vector entries, so on. Wires visualize the amplitude and phase changes in intermediate calculations, and as well as to visualize the entries of a matrix. Quantum gates are the theme of Quantum Odyssey, just as in quantum computing. They are analogous to logic gates, and they allow you to manipulate qubits to implement entanglement and then quantum computing. We will demonstrate the example of the Born rule and the qubit gates and how this leads to linear algebra. On the left is a 1 qubit gate, so 1 qubit single gate. Over there, notice that it's a bow type shape. It's called a bipartite graph, and there are 4 line segments. 2 of them are, let's say, are straight. So let's say straight. And the other 2 are cross. The blue entry is the left from the left. The B is, let's call this the B is the left from the right, so that's yellow. So sorry, I got the colors wrong this time. The green is the right from the left, so, and then the purple is the right from the right. Here's a 2 qubit case, so 2 qubit. The slots, let's say the states are namely 0, 1, 2, 3. You can write them in decimal, you can write them in binary. And we will express this in a matrix form. Basically, we have reduced quantum computing into linear algebra. This is a considerably more involved example. However, we have the diagonal terms as, let's call this alpha. We have beta. Let's color code them. Gamma. We have delta. Now we consider the colors of the wires. So let's call this M, 0 from 1, M, 0 from 2, M, 0 from 3. So these are row-wise. That means it's the 2 is from it's the same. The output we're representing to the same output. Then we have m1 from 0, m1 from 2, m1 from 3. Let's do the same for the position 2. So we have m2 0, m2 1, and then m2 3. Lastly, we have m3 1, m3 2, m3 3. We now consider, let's try this. Let's try A, B, C, then D. So X, Y, Z, W. Let's do this again. So we have X, Y, Z, W. At the end, we conclude that psi of 1, so state, after is the matrix times the state before. This is where the Born rule comes into play. The Born rule states that the probability of observing, let's say, state x, let's say that's one of the eigenstates, provided the system is in an arbitrary state psi, so it's like a set of sigils, is you take the inner product, then take the absolute square norm of that. This is the same as, let's say, finding the area of a sigil, in which the probability amplitudes are equivalent to the radius of the sigil. So amplitude is to r, while this is to probability, which is to the area A. So now I taught you linear algebra without saying the word matrix, or like introducing you to matrices first. Okay, so we will provide you with some of the most basic quantum gates, because these are the Pauli gates, and then there are the basis change gates, as well as a control gate. The X gate is the most basic one that is not the identity gate. Its matrix representation is ones on the anti-diagonal. Basically, the 1 comes from the 0 slot and the 0 slot from the 1 slot. The Z gate is next. The Z gate is represents a diagonal matrix. That means there are no cross terms. The one on the left, that means let's call this the equivalent to the 0 state respective to this particular qubit, or the positive eigenstate, would not get a phase change, but the negative eigenstate would. The Y gate is the most difficult of the three. And of course, it's the last one to be taught. The one going left, that means from the 1 to the 0 for that qubit, also loses, let's say, goes backwards a quarter turn in the phase diagram. So it's yellow, or -I. complex numbers, the imaginary unit, are akin to a rotation. In fact, they are used to algebraically express rotations. And the wire going from the left to the right is positive I. So once again, we have left from right. This is right from left. The H gate is like almost like an all ones matrix, but except the right diagonal member is, however, made negative. So 1, 1, 1, then negative 1. However, we also need to consider like a factor to ensure that the split is even. And we are doing it by the radius. So when the area is halved, the radius is by a factor of 1 over root 2. The H gate is commonly paired with the C gate, called the control operator. So that's technically always comes with another gate called the C gate. It's not commutative in respect to parallel operations. C gate and the H gate and the X gate together create entanglement. So the C gate is of the form 1, 1. So then we have alpha, beta, gamma, delta. So let's change the color to say it's alpha. So left from left, left from right, right from left, and then right from right. In this case, it's a 4 by 4 matrix in the smallest case. And then there's the P gate. The P gate is a generalization of the Z gate. The first P gate you will see is the S gate. Then there is the T gate, and there's more variations. It's also like a diagonal, but except this time it's 1, and then there's a rotation along the unit circle, so that's e to the I theta. We will discuss more about P gates once we get into rotation matrices, which allows the implementation of x, y, z's and their powers of these gates. So this is the P gate. Other gates you will see are the SX gate, which has a property of if you apply SX twice, it makes up the X gate. And then we have the R gate, which is like a power of one of these 3 polygates. And then finally we have the I gate, which is just the identity operator, the no op. Let's go back to the rules again. And then we see that we first apply the H gate. So we can write this algebraically, but please be aware it's from right to left. We have H gate, then we have Y gate. So H gate, the H on the ground qubit, y on the ground qubit, and then we have the C ground x1, x2. Notice that, and then we apply it on the psi. Let's call this psi is equal to 0. So zero state equals, let's something like this. This is basically like a variation of negative I. Then we have the Bell state minus on 3 qubits. So we already created an entangled state from this example of rules. And moreover, this thing is actually equivalent to C0 then x1 tensor x2. But you can also write it this, except this time this looks serial, while this looks parallel. This is again, you can collapse a serial operation into a parallel operation, provided that the controls are the same in this game. So serial and parallel. We end this session with a sample. So just give like a minute to reflect on what you have learned, what familiar stuff you have an impression on that became more clear by watching this video, and what do you want to get out of it from Quantum Odyssey after playing this, and either like downloading the free version, the early free version, or paying the, let's say, $20 for the current Steam version. So here is our sample. So on the top row is the adders, which will be featured on Quantum Odyssey. On the left is the half adder. On the right is the full adder, which can be combined into 2 half adders plus OR gate. OR gate on the ANDs. So we apply a half adder on the inputs, then we apply another half adder on the 2 carries, then we apply OR on the ANDs. So half adder AB, half adder CC, then OR AND. That's my mnemonic for that. On the bottom row is the visualization of the quantum Fourier transform. So it's a sequence of triangular operators. Okay, the qubits are now bit strings. We apply a sequence of CT gates. The T's are successive roots of the Z gate, except the very first tip is always an H gate. We do this repeatedly with the J1s being the top qubit being applied, the T, then we successfully apply the next bit, so on, until the last one is done. And also the more distant the distance from the C to the T is, then the higher the order of that T gate is. So it's just plain mnemonic English definition. And then we finally perform a swap between the first and the last qubit. And then therefore it turns the state into like a 0 plus, like, let's say, a bit string multiple of a turn of the one state. So QFT, that's the quantum Fourier transform. And that can be expressed as a matrix. And let's say the rows are, let's say, omega ijk. We will explain both of them in one of the later videos on quantum phenomena. And of course the classical gates as well. So notice classical gates can also be expressed as a matrix. So namely the low high from the combinations of input. So for the classical gates, it's on if like any of them are on, so any. For the AND, it's all. This is the XOR, that means one, but not both, either. The NOT gate is equivalent to the X gate. So the X gate is commonly also called the NOT gate, and then there's a C NOT. The NAND, which is a universal gate, so you express any of these classical gates using only NAND as the inversion of AND. So you apply a NOT after the AND. But that also becomes matrix multiplication. So we have, and this works, the dimensions match. And in algebra, the order is opposite, so it's the left is applied last from the right compared to the diagram from the left to the right. So this is some sample of what you will learn in Quantum Odyssey and what Quantum Odyssey has to apply to everyday computer science and the computer science material that's behind how electronics operate. Do you see the pattern? And of course, I conclude the session with a like and subscribe. Like and subscribe to my videos, and also support me on Patreon. I am reinstating my Patreon, and with that support, I'll be able to create these videos on a regular basis. It took me over 2 hours to make this, excluding the, let's say, the prior knowledge and the rehearsals and retakes. So like and subscribe to my videos, my channel, and support me on Patreon. Make this 50-day a blast. 50-day for 2026. So, see you mates. Me checking out.